Okay, so good morning, everyone. It's a pleasure to have Gustavo Wiederhecker here with us today. Gustavo completed his studies at Unicamp, both his master's and PhD. Then for his postdoc, he went to Cornell University, and then he went back to Unicamp, where he is a professor now. He works with integrated photonics, and in particular, nonlinear optical effects. It's a pleasure to have him here today, to host him in our colloquium. And he will tell us a little bit more about his work. So please, Gustavo, first of all, thank you for being here, and the stage is yours.
Okay, thank you. Thanks for the nice introduction, Marcia. It's really an honor and a pleasure to be here. It's my first time at IIP, but not the first time in Natal. So when I was young, I actually had an aunt that lived here. So this was the first time I got in contact with echinoderms and crustaceans. And I think for all kids, this is the maximum joy that you can have. So really, I came to Natal actually 3 times when I was a kid. And you can imagine this is just paradise, right? So I have really good, probably one of the best trip memories in my life are from this place. So it's really nice to be back here. I hope I find some. You used to find crabs on the beaches back then. This is 1989. I don't think that's no longer the case, but anyway. Okay, with that, let me move on to the science. There's a. Let me see. And I'll be talking about how we manipulate this interaction between light and sound, and also other nonlinear interaction that occur when you put very strong electromagnetic fields in materials, and what kind of things we can do with that. So I'll be discussing 2 examples as showcases of the possibilities in this area. So just to put the evolution of this field is really due to the demand that there was for a long time in building up a very long-haul infrastructure for optical communications. That's what really poured money into this field and allowed it to evolve to the point it is today. So if you're not aware, this is a map of the long-haul optical fiber links across the world. And last year, we celebrated 5 billion kilometers of deployed optical fibers worldwide. This is about the distance from the sun to Pluto. So really, we are in the astronomical length scale for optical communications, and thus there's a lot of demand for technology to enable this sort of infrastructure. And it continues. It gives us the impression that all these long links are installed, so there's no more demand for fibers. That's not true. Actually, there is 10 to the 8. 400 million kilometers of optical fibers produced every year. So the game continues. There's only one thing in the world that beats a wire technique that beats optical fibers, which are spaghetti. So if you take the data from wheat production worldwide and compare that with the Italian consumption of spaghetti number 5, you're going to find that Italians actually eat more spaghetti than optical fibers are produced worldwide every year. Anyway, just a note on that, and this has moved now from long-haul communications to these data centers, right? We've been asking very useful questions for this AI chatbots, and to answer those very important questions we ask every day, we need infrastructure. So if you go inside one of these data centers that are processing our GTP and other cloud infrastructure, they look like that, and they're full of optical fibers. These are the colored wires over there, but also devices that convert light into electricity, process light, route light, and this has been done using this technology that I'll be discussing with you today, which is integrated photonics. And there has been a recent increase in interest in enabling these technologies, because if you look how these large language models that we've been using every day are scaling, this is a plot showing the number of pounds. Sorry, I pressed the killer button here. The number of pounds of CO2 emission for typical daily experiences, you're going to find that, for example, an American takes about less than 20,000 pounds of CO2 a year. A car, if you're worried about your footprint, right, takes about 100,000, including the fuel that you use every day. But when you go into training one generation of ChatGPT, we are talking about spending about 600,000 to 700,000 tons, 1,000 pounds of CO2. So be mindful when you ask questions to ChatGPT. The footprint is larger than you think. But anyway, there's hope that optics might bring functionalities that will allow these systems to reduce significantly their energy footprint. And this is one more industry drive to this area. I'm struggling sometimes with the pointer here that do that. Okay. So let me go down to the physical layer, right? So what we'll be talking about today is really structures that confine light in very small scales. So I'm comparing here two structures to give you a sense of scale. On the left, we have an integrated photonic waveguide that guides light by total internal reflection, as you learned in the high school. These are usually structures with a typical footprint of about 1 micron, the cross-section. The refractive index contrast, though, to confine light in such a small scale, remember this length scale here is considerably less than the wavelength of light that is used in this structure. So we are in the sub-wavelength guiding region, and this requires you to have a very large index contrast to be able to still trap light in these structures. And if you compare that to the optical fibers that are just mentioned, typically the light is confined to about 8 to 10 microns region. The refractive index on the other side is a very small, very low refractive index contrast. And if you put these two guys in scale, that's the actual scale between both, and the area of the optical field in optical fibers relative to waveguides is about 200, factor 200. This means that the intensities of light that you reach in the left side are much higher than what you can usually reach in optical fibers. And this brings the field of optical nonlinearities to the game. So for example, if that's one aspect you can find very strongly diffuse. The other aspect that because you have such large index contrast, you can bend light over 90-degree bends. This is something usually that you don't see with optical fibers. Optical fibers, if you bend them, you lose most of the light. Here I'm showing a picture in our lab of a 50 microns band radius waveguide. So this is about a 5 millimeter scale here, and light goes in green and completely turns a band here without a lot of significant losses. So this is allowed because of the very large index contrast that you have. And this allows you to actually wrap these waveguides around and build these very long structures in a sub-millimeter or sub-centimeter spatial scale. So you can put meter-long waveguides into a very tiny chip. This allows to get very long, effective nonlinearities as you accumulate the nonlinear phase through the propagation in the material. The other thing you get is a manipulation of spatial modes. So you can think of these waveguides as quantum wells, and you're putting the depth of the quantum well larger and larger. This allows you to actually host much more optical modes or optical states inside the waveguide. So I'm here showing this animation, the wave vector diagram that you get for the structures, frequencies versus wave number along the propagation direction. And you see that as I increase the core refractive index up to 3.45, which is a typical value for silicon, for example, you actually get a set of modes that allow you now to manipulate this spatial degrees of freedom of light into this photonic integrated structures. The third element is, well, if you can bend light and you can have large intensities due to the tight cross-section, you could also probably build resonators out of this structure. So if you wrap them around, you actually can get resonant cavities that allow you to enhance the intensity of light through constructive interference when light hits. The wavelength of light is a submultiple of the length of your resonator. And the result of that you get, if you look at the transmission of this resonator, how light's as the light as a function of frequency evolves, when you get close to these resonances, you see that you have these very sharp deeps, and the sharp deeps are nothing but resonances separated by a given frequency scale that's related to how long light takes to make a round trip in these cavities. And just to give you a reference, the intensities that you reach in these resonators are in the order of 80 megawatts per square centimeter if you shine a 1 milliwatt laser, which is about the laser intensity of this field. So you can have a sense of scale. If you reach 30 petawatts, you completely ionize the material, okay? So this is much weaker than what you would need for ionization, but large enough to induce nonlinear response of your material. So the name of the game here is really to explore this confinement, to excite, read, control linear and nonlinear properties of light, and let's see what we can do with that. So over the last, let's say 10 years, there has been a spur in this field with several applications. I'll give you some examples here. People have demonstrated using these very chips multidimensional entanglement for photonic quantum computing. People have been generating squeezed states to pursue Gaussian boson sampling to perform also non-universal quantum computation. This is a work by the group of Paulo Nussenswein at the University of São Paulo. They're doing quantum frequency conversion. If you need, for example, in a quantum computer to convert the frequency from an ion trap quantum computer into perhaps another telecom wavelength frequency so that you can send this stationary photons into flying photons, stationary qubits into flying qubits, you could use this sort of technique, all again using integrated photonics, and also build the so desired turnkey entangled photon sources also based on this technology. More recently, that connects also to the point that I raised, that you could use these techniques to reduce the power footprint and demand that you have on standard data centers. There have been recently work on using these devices to build what we call coherent Ising machines. These are coupled resonator systems that emulate a Ising Hamiltonian. And by doing so, you could probably, people have been working on trying to solve NP hard problems using this kind of structure. Okay, so it's really a very diverse range of applications that this has been explored. So I'm going to tap into two examples in this talk, one related to Kerr nonlinearities and the other one related to what we call light-sound interaction or optomechanical nonlinearities. So just a bit about the Kerr. So the idea here is that you're going to take one of these ring resonators that you built using integrated structure. You're going to pump this with a single frequency laser. And if you get the right conditions, what can happen is you get a rainbow out of the system because of nonlinear response of the materials. So the idea is you have a pump. All these frequency grids here are modes of your resonator, right, separated by the cavity round trip length. And if you have this right size of nonlinearity, the pump starts to transfer energy, create pairs of photons that will populate all these frequency modes. So this is what we call the optical frequency comb. The origin of that, if you mind, it arises from what we call the Kerr effect. The Kerr effect is nothing but the fact that the nonlinear polarization of light has the polarization induced by electric field in matter has a linear term that gives rise to refractive index, as we know, but you also have at high intensities nonlinear terms. So for example, the third order nonlinearity, which happens in all centrosymmetric materials, leads to the formation of new frequencies. So for example, I'm applying here an harmonic motion of this electron. Let's say it's an electron trapped in an atomic potential, and even though it's performing a linear motion, due to the nonlinearity of the polarization, you get a distortion of this oscillation, of this polarization. And if you can make a Fourier decomposition of this nonlinear form, and therefore you get new frequencies, okay? So that's the idea behind this Kerr nonlinearity per se. And there are classification of different effects that arise in the system. Some are called, for example, self and cross-phase modulation. This is a situation where light changes its own refractive index. So light is propagating, but is changing its refractive index due to its intensity. There's also cross-phase modulation, where light changes the refractive index of other frequencies propagating along the same structure, and also four-wave mixing, which is a class where light energy is transferred from one mode into another mode. And this is precisely the effect that gives rise to this phenomena here. And it's an interplay between all of them. So just for you to get a more clear picture on this, how these different effects come together. So on the first end, as I pointed, there's linear dispersion. The refractive index depends on frequency. This means that each optical field propagating along the structure is traveling at a different phase velocity. And therefore, instead of getting a frequency grid that is equidistant, what you usually get in this structure is a structure that changes with frequency, which is this one. So we call this anomalous dispersion or normal dispersion, depending on whether the distance between the modes is increasing with frequency or reducing with frequency. This is a consequence of linear optics, okay? Just the fact that the refractive index changes with frequency. And by the way, at any time you may interrupt me if you feel that I'm going either too slow or too fast here. More important to convey the message than to get to the end of my slides, I would say. So this is dispersion, linear dispersion. But you also have, as I pointed, cross-phase modulation. As you put light into this resonator, it changes the nonlinear response of electrons and starts shifting the refractive index perceived by all other fields propagating along the structure. So it's pictured here. I'm increasing the pump power at a given resonant mode, and as a consequence, all the other modes are shifting along. So now you need to play around with these two effects. On the one side, linear effect is detuning your equidistant frequency grid, and the nonlinear effect is pulling them back. So the question is whether you can balance these things. And there's a very fine spot if you can compare dispersion, linear effect with nonlinearity, and these two effects, if properly managed, they will lead to gain for this other mode. So the pump light will transfer energy, serves as a gain media for the other frequencies propagating in this structure. So let me make an animation just to make it clear. I won't dive into this dynamics here, but just to picture that there's an equation that governs this. It's called Lugiato-Lefevre equation. It's similar to the nonlinear Schrödinger equation of the Gross-Pitaevsky equation. It has the same family of solutions. It admits soliton solutions and so on and so forth. But the key point here is I'm showing you here in animations, so you don't need to dive into the details, but you have dispersion effects, you have nonlinearity, you have detuning between your pump field and your resonator frequency, and you have the strength of your pump field. And what happens is, I'm going to show in this animation, I'm tuning my pump towards one resonance. And I'm showing you the two effects that I just described. The self-phase modulation, the fact that this mode is now shifting as I try to get close to it. So this is my laser frequency. And there's another mode, actually the whole set of other modes shifts as well. It's actually shifts by twice the amount that the fundamental mode shifts. So this is just a difference between the magnitudes of self and cross-phase modulations. And these are very important because I need to now, the dispersion causes one effect, and this cross-phase modulation effect try to runs away from it or compensates it. And if I get things right, if I design my structure right, if I've got the right cross sections, for example, right field intensities, I can balance this thing. So I'm going to show you a sequence of animations now that gives you a glimpse on the reach dynamics that this sort of nonlinear equation dynamics provides us. So follow along. So I'm going to show you these 5 plots. What I have here is on top, I'm going to show you the field amplitude across the resonator perimeter. So -1 to 1, you're giving a full round trip on the resonator. It's a spatial domain plot. On this middle plot, the colors here, the red colors are more intense, the blue colors are weaker. This is in dB scale, so it's a very wide range of intensities. And in the horizontal axis of this color map, I have wavelength of light. So I'm spanning a full octave here, going from 1 micron, a little bit above the visible region, up to 2 microns. And I'm going to pump right in the middle here. And I'm showing the vertical axis, the pump detuning is the parameter that tells you the distance between your laser frequency and the resonator mode, of one of the resonator modes that I'm driving. So let's go along. And just for reference, I'm showing a line scan of this plot. So if I make a line cut here, that's what I'm showing here. And showing here just for reference that the dispersion is anomalous in this case. So the concavity of this parabola is upwards. If it's normal dispersion, the concavity is downwards. Anomalous dispersion, concavity is upwards. It's just the sign of this coefficient here. So I'm operating the pump in the anomalous dispersion regime. It's a regime where cross-phase modulation can cancel out the effect of linear dispersion. So let's go. So I'm scanning my pump, far away from resonance, just a single peak. And as I get closer to resonance, energy builds up. And if I stop at a given detuning, what I have is actually a formation of a series of laser lines that were transferred through 4-wave mixing process into other modes, and you got what we call the Turing rolls. Okay, so it's very, very well behaved at this regime. If I keep further pushing my detuning, increasing the laser intensity, I get into a chaotic region where light intensity is fluctuating all over the place, and I generate a very wide frequency combo. You see that this spans a full octave of frequencies. Right? A full octave corresponds to twice the frequency. So if I pump at omega, I generate lights all the way up to 2 omega. But if I keep going further, something really interesting appears that out of the scales, I starts to show some order. So order is reestablished. And actually there's a region where I form a set of very well-defined pulses that are propagating in this resonator. And these are called soliton molecules. Each of these pulses is a soliton, as a wave that propagates without dispersion, without changing its shape in time. And as a result, they are interacting among themselves. That's why they're called molecules. But the most interesting spot comes if I keep pushing this up to the very point where I lose track of my optical resonance. But at this point, I get a single soliton propagating around the resonator, and the spectra is extremely clean, as you see here. I get a very full octave spanning frequency combo. And this can be used for all sorts of applications, including spectroscopy, including entangled states generation across multiple frequency bands, and so on and so forth. Or even as a source for telecom lasing. You can use each of these comm lines, for example, as an individual laser to convey optical communication signals. And even though I put this, it might sound that this is very tricky to get. It turns out that if you look at the literature, all different kinds of micron scale resonators do that. Here's just a series of microscopic images showing you the different shapes of these resonators. And the message here maybe is, well, don't oversell this. It turns out that if you get just the right material and make it small enough, you will get this sort of dynamics for you to explore in the lab. So there's a very rich, very vast options of devices that you can use to explore these effects. Actually, recently people have demonstrated that you can operate all of this within an AAA battery. So there's a battery pumping a laser, the laser is pumping a resonator, and the resonator is generating their frequency comb. So these are battery-operated optical frequency combs that fits on the palm of your hand. So this is not very complicated setups, if you will. We did a lot of this research in Campinas, different aspects of this that I'm not going to dive into the detail, but one of the key things is understanding, for example, how you broaden the spectra. And you find that there's this peak here, for example, that's related to soliton, that's called a Cherenkov radiation of light. So you're actually transferring energy to a very far away frequency mode, in analogy to Cherenkov radiation that happens when you shine electrons in a material or beta particles in a material. So if you understand these things right, you can get this very wide, very broadband frequency combs. Okay, so let me just remember you that not all nonlinearities are of the type chi3, and perhaps the most popular one in quantum optics, for example, is quite chi2 nonlinearity, where you explore the quadratic effects of the electric field. The reason it is not so popular in integrated photonics is it requires you to have non-centrosymmetric materials, like crystals that don't have inversion symmetry. And this is, of course, restricts the material options that you have. But you can still find them. A lot of the LPO community in Brazil, like Paulo Souto Ribeiro at Santa Catarina, or the people at UFRJ, they all use this sort of chi2 effect to generate photon pairs and entanglement through this process. And the reason you get, I don't want to dive into the entanglement, but I want to recall you why this is interesting. One of the things that this nonlinearity does is allows you to convert a given frequency of light into one photon of light at a given frequency into identical photons at half of the frequency. This is called spontaneous parametric down conversion. That's the name for it. And the dynamics of the signal fields as a function of the propagation length in your material follows an equation like this. So this is, think of this as just a parameter that's controlled by the pump intensity, so I can tune it up or down by controlling the number of photons that I'm shining in, but it couples the field amplitude to its quadrature, right? So when you have an equation like that, you can think mathematically, well, if I write this A as x plus IP, the two quadratures, I'm going to find that one quadrature grows with a positive coefficient, the other quadrature is reduced with a negative coefficient. So one is amplified, the other is de-amplified. This is what we call squeezing of light, okay? So an example of application so for squeezing is building what we call this parametric oscillator. So a good example of parametric oscillation is a pendulum, right? Or a swing that you drive. In order to get the swing to oscillate, you need to pump it at twice the frequency. You go up and down while the swing has just gone one half of the cycle. And then you go up and down again in the other half. And you do it again. If you do it right, you amplify your parametric oscillator, your swing. So if you couple two parametric oscillators, for example, you're going to find that they are either in phase or out of phase. And the phase relation between them is determined by the intrinsic fundamental noise that drove the system out of static equilibrium. And in quantum mechanics, this is due to the zero-point motion of these two oscillators. So this has been used, for example, for generating random numbers explored on this true random nature of the zero-point fluctuation of these optical fields. So because of this quadrature coupling, another way to see this is look at the phase plates, the Glauber diagram for this. If you look at momentum and P and Q as the two axes of this plot, if you increase the pump power, your S, you're going to see that initially you get a squeezing. But after some point, you have a bifurcation where the energy transferred from the pump to the signals is larger than their loss. So they become an oscillator, a coherent state. And that's what you're seeing here. You start with vacuum state, you squeeze the vacuum, and after you reach this threshold, this bifurcation point, you're going to find two coherent states, one that's along the positive x-axis, the other one is along the negative x-axis. So they are pi out of phase. That's the two phases that I exemplified with the pendulum. And the reason this is interesting is that whether you're going to get a pi phase or a zero phase is truly random because it depends on this zero-point fluctuation of this system. Okay, this is great, but it requires, as I pointed, these very special materials, these very special crystals that are not always compatible with integrated photonics. Okay, so what about trying to do that with Chi3, with a third-order nonlinearity? In third-order nonlinearity, what you can do is actually, instead of pumping with one laser, you can pump with two lasers, two pump frequencies that are non-degenerate, they're not equal in frequency, and explore what happens when the two emitted photons, signal and Euler fields, are degenerate. If this happens, you can actually mimic what I just described with Chi2, but now the strength of the nonlinearity is given by the product between the two pumps. Okay, so you can do that just to say that you can get the same field coupled to its quadrature dynamics by mimicking a Chi2 effect, but now in a material that you can access with integrated photonics, like silicon, silicon nitride, silicon oxide, materials that are readily available for doing integrated photonics. That's what we want to go. And as I pointed out, there's this frequency comp issue, let's call it this way, because if I pump two pumps, each of these pumps, through that very process that I described, will start cascading into all other modes. The other pump will do the same thing and becomes really a mess, even you get chaotic behavior and etc. So what we wanted to do is, this is a picture from the lab. What you see the two pumps, blue pump, red pump. You see the DOPO in the middle, but you also see these other sidebands. Each of the sidebands is sitting at one of the cavity modes, one of the cavity frequencies. And this is the bifurcation that I just described. As energy grows, you eventually reach this bifurcation point. It's sort of a Hopf bifurcation where you get a positive phase and a negative phase state, right? These are the two binary phase states that you get from this OPO. What we wanted to do is get rid of this spurious effect. On the quantum side, they generate correlations. So you no longer get, if you look at squeezing, this squeezing is distorted because you're also creating correlations between this field and all the other fields. So how can you build a structure in integrated photonics that suppress all these undesired processes, but keep the one you want, the one that generates a very high fidelity, a very high quality squeezed state. Just to show other people have been working on this too, and these spurious signals, they always appear, and they limit how much squeezing, for example, you can achieve in one of these central modes, which is what we desire. And the various applications for that, just to recap, are if you operate above threshold, you can use this to generate quantum random numbers. Here's a sequence of pulses from Alizera Marandi and Rob Beyer group at Stanford showing that you can get a sequence of optical pulses whose phase are arbitrary sweeping between 0 and pi. And if you put this through interferometer, you get a sequence of pulses that are truly random in nature. You can build the coherent easy machines because this phase can be associated with the two spins. Phase 0 is one spin up, phase pi is spin down, and now you couple these spins and you can emulate a network of coupled spins using this kind of systems, that the coherent easy machines. And as I pointed, what we are interested now is this below OPO threshold, which is generates squeezed states. How we do that? Okay, that's what I want. I want to get rid of all these modes. And this brings the concept that I just mentioned in the abstract. It's a photonic molecule. So what the hell is a photonic molecule? Let's say if you bring two resonators close together, they're coupled through their evanescent field, pretty much like if you bring three potential wells together, you're going to have a frequency splitting, right? Hybridization of the eigenvectors. And for this particular nearest neighbor coupling system, you're going to get three eigenmodes. That's the nearest neighbor coupling. So three resonators, omega 1, omega 2, omega 3. They couple to each other in the nearest neighbor approximation. So these two guys are coupled, and these two guys are coupled. That's why you don't get this off-diagonal terms far here. And what you get, you're going to get three eigenvectors. And if you ask how they look like, you can do electromagnetic simulations and show that they look like this. One is a very symmetric shape. The other one has two outermost rings lighting up. The other one is dark in the middle because the phases are opposite here. So there's constructive interference, destructive interference in the middle. And you get this super antisymmetric state that is shown here, which has the highest frequency of all three modes. So when I do that, what I'm essentially doing is I'm creating a spectra that the frequency scale of separation now, instead of being the free spectral range, every time light makes a round trip in these resonators, I'm creating a frequency scale that is controllable through the interaction strength between them, so how close they are together. And by doing so, I create my triplet states that I need to enhance that dual pump interaction. So I can pump on the blue, on the red, and look what happens in the middle here without worrying about all the other modes in the spectrum. So this is a picture of the chip in Campinas. So we built these chips. They have three resonators here. Each of the resonator has a controller pad. It's a heater. It's a micro heater that changes the chip the resonator temperature and allows you to dynamically shift their eigenfrequencies. So it's a fully controllable chip that allows us to play around. This is experimental spectra showing how they look like in the lab. So here's a typical experiment. I'm not going to dive into the details, but the essence here is I have a tunable laser. I can get this tunable laser to be modulated, generating my two drives. So this is an amplitude modulation of the laser, generate two sidebands, and these two sidebands are amplified. Their polarization state is controlled, and then I send them throughout the chip and look at what happens in a spectral analyzer. That's the basics of this experiment, okay? So that's how it looks like. You have three frequencies. These are three supermodes that I just described from a photonic molecule. I don't need to care anymore about the other states because they are not going to be phase matched to my 4-wave mixing process. The frequency distance between them is very different from the frequency distance between the two pumps, so I don't need to worry about them. They exist, but they're not, the energy is not conserved for their interaction. So that's what I get from this electro-optic modulator. I get the two carriers and a sideband. These are the two pumps that I'm going to use, so I can control them with our RF frequency source. And I'm going to sweep these two guys towards these resonances and see what happens. So this is what we did in the lab. Essentially, a very simplified manner to describe, but still gets the whole idea. And when you look at the experimental trace, let me show you what we see. So this is an animation showing summarizing the experiment, which shows in color is the spectral intensity, right? So we're seeing the two pumps here, very strong, driving by. I'm detuning them simultaneously, as I pointed out in the animation. And I'm looking at the spectrum, trying to see what happens in the middle. And I see that when I get close to resonance, I start from the vacuum field, and this vacuum field is populated, goes above threshold, and I get my degenerate optical parametric oscillation right in this guy. And I can control the strength of this by just tuning this to this micro heaters that I have on the chip. So in summary, for this part, that's what we did. We generate this, we suppress this degenerate 4F mixing. We generate very strong optical parametric oscillation here that can be used for this frequency random number generation applications, but also for squeezing. That's something we are working on right now. Actually, we just did some experiments in Campinas where we show that you can actually squeeze light if you operate below threshold. And this is sort of this intensity plots here showing that as you scan the quadrature of your local oscillator, you reach a point where you're barely in the squeezing regime. We're still working on this, is unpublished data, but we have initial signs that this state is being squeezed. The trick here is that there's losses, so the state is squeezed, and you gotta make sure you extract all the photons from the system to not lose your squeezing. And this is something we're working on right now, is to address these losses that we have in the system to make sure we can measure a net squeezing out of the chip. Another area that we have been looking is symmetry breaking. I'm not gonna discuss in detail, but essentially, you can look at the nonlinear dynamics of the system, and what's really happening is that the two pumps, they lose stability and their intensity changes, and this can be mapped into a symmetry breaking process. So there's a very rich physics on top of those cascading effect that I described before that we've been exploring, and this is something, if you guys are, someone here is looking into symmetry breaking physics, I'll be eager to talk to you about it and discuss possible collaborations on this topic. Okay, so I think I give you just one example. I'm not going to dive into the easy machine. I thought Rodrigo would be here. That's why I wanted to talk about the easy machine, because I think you know, he's a person that's been working really hard on this easing Hamiltonians and more general models. So I think this is one area where there could be a very fruitful collaborations in having an experimental platform that allows us to, in the lab, study how easing Hamiltonians behave. And I'll be eager to, you know, discuss and find, build devices that allow you to explore different types of couplings in easy Hamiltonians and so on and so forth. This is a very active field of research recently, I must say. Also, just to give a note to Rafael, this can also be explored for entanglement generation. So this is a situation, this is a paper from Alberto Morandacci group in Canada, but this we now have this single photon detectors in Campinas that were recently purchased that allow us to measure what is the count rate of single photons being generated in each of these modes. And this can be shown that you can have multidimensional entanglements for Q-trits and Q-dits generation. So this is something that also we could discuss in possible collaborations using, in this case, for example, time beam entanglement. Okay, so this closes on the care side of things. Let me show you a little bit another side of the same story, right? And let me just show you why. We've been seeing in the literature all these different approaches to quantum computation, different kinds of qubits being implemented. Most of them are stationary qubits. They need to be sitting at a place, like the superconducting resonators, qubit-based, this ion trap, neutron atoms, all this kind of approaches are stationary qubits. They have the advantage of being very controllable. They interact very strongly with your control parameters, but they are also very bad at being transported, mostly because many times, for example, in case of the superconducting qubits, they operate at gigahertz frequency. In gigahertz frequency at room temperature, they're flooded with noise. So the thermal occupation at gigahertz frequency is very large, right? So a good number to have is to have an occupation of one quanta of excitation, you need to be at about, for 10 gigahertz, so you need to be at about 100 millikelvin, right? So you cannot transport a stationary qubit or a photon that is operating at that frequency without being flooded with thermal noise, unless you make a cold communication link. So how you bridge this, how you connect this stationary qubits operating at gigahertz frequency or even at ionic frequencies like visible frequencies for ion traps to other qubits that are sitting elsewhere in the lab. You're going to use light, right? So the goal of this part, perhaps the motivation that we've been shooting for, is to find a system that allows us to bridge the optical domain with the microwave domain, right? So what you want to do, let's say you have two dilution fridges with superconducting qubits, how you connect them, right? So you're going to need to convert to optics, propagate light, and then convert to microwave again here. So these transducers are what drives us in investigating this optomechanical interaction. So what you want to have is a resonator, optical resonator system that has some loss, a mechanical resonator system that also has some loss, and a microwave resonator. And we're going to couple a mechanical element into the microwave resonator and a mechanical element into the optical resonator. And this is going to be a bridge to convert microwave to optics. So we did various different attempts in that direction. I'm not going to dive into all of them, just a few references from our lab here. I'm going to give you just one example of recent results that we are pushing for in this area. And if you're not familiar with the field, let me give you a one-slide introduction, what we call this cavity optomechanics. So the idea here is, let's say you have a cavity of some sort, optical cavity, right? This could be also a microwave cavity. And you have an object that is oscillating in the near field of this cavity. It's going to perturb the optical field, as I illustrated here, right? And as it perturbs the optical field, it modulates its frequency. As a result of this modulation, the transmission of your optical cavity, as measured by the laser here, is going to oscillate back and forth. So essentially, we're encoding the mechanical motion into the amplitude of the photons stored in the resonator. This is the mechanism by which light couples to the mechanics, and also how the microwave couples to the mechanic. It's a time-dependent perturbation of the mechanical oscillator into the optical domain. And the optical oscillator has a finite loss, so it has a finite bandwidth. And if the mechanical modes are sitting further away from the resonant width of your optical mode, means we are in what the so-called resolve sideband regime. With this resolve sideband regime, what I can do is I can choose whether I'm going to create phonons, which is a Stokes case, right? Light is scattered towards a smaller frequency, and this extra energy that's lost is converted to the mechanical system, or I can focus on changing energy to the anti-Stokes case, where light gets an upshift in frequency, and by doing so, it destroys a phonon. So I can operate my system either in this phonon destruction regime or in this phonon creation regime, right? And I'm not going to dive into the details, but essentially this means you can operate with a beam splitter, Hamiltonian interaction, or a squeezer Hamiltonian interaction. And this is the basis for all the results that I'm going to describe later on. Again, this is not only us racing for this. There are many groups working with different kind of optical cavities, different kind of mechanical waves, and different kinds of qubits, right? And the idea is to find, the name of the game is to find what is the best platform to perform this, right? We haven't yet reached this part. So our group have not yet managed to build on the same chip microwave resonators that allow us to couple to the microwave qubits, but this is something we're working on with collaborators right now. So we've been focused on optimizing this part of the process. For example, how these things look like in real life. So this is a silicon-based nanophotonic structure that traps light. So this is a Bragg mirror for light. So light is stored in the center of this resonance, but it is also a Bragg mirror for mechanics. So mechanical waves get trapped in this structure. So this is a 10 micron scale bar. So this is a very thin, a thousandth of a human hair width resonator that traps both light and mechanics. And mechanical waves are radiated through this Bragg mirror, and part of it couples to this piece of lithium niobate, which is a piezoelectric material. And as it gets shaken by this mechanical wave, it produces an electrical signal. And this electrical signal is captured by these two copper wires, these rhenium wires, and these rhenium wires are eventually coupled to a microwave resonator. This is how it looks, right? It's as complicated as that in terms of microfabrication processes, but this has been done. This is work by Simon Groblacher groups at Delft University, which we have a collaboration with. Actually, there's a company, a startup company in Delft producing these things for commercial applications, if you can call quantum computing a commercial application nowadays. You can do all sorts of tricks. You can entangle microwave mechanical modes at gigahertz frequency to light. This is work by Thiago Alegre at Unicamp in collaboration with Simon Groblacher, where they created an entangled state between a microwave photon and an optical photon. Okay, so let me show you to close one full device that we've been working recently that's based on this technology, on this light-sound interaction. And this is often called in the solid-state physics literature as a Brillouin scattering process, right? So the idea is I'm going to come with a pump field. This pump field, optical pump field, is going to interact with thermal phonons that are sitting in my material. There are phonons at all over frequencies. Some of these phonons will scatter light, right? And because I can think of phonons as traveling gratings for light. Essentially, they are modulating the refractive index, and these refractive index modulations are traveling through the material. So these are like Bragg gratings, and they scatter light. But because these gratings are moving in time, in space, they scatter light with a Doppler shift that's related to the velocity of this grating. So the frequency of the phonons is impinged on this scattering process through this Doppler shift. And what you usually see are the two sidebands that I called earlier, Stokes and anti-Stokes. Stokes is when a phonon is created and a photon is absorbed. Anti-Stokes is when a photon absorbed and the phonon is created. Or it's when the grating is moving towards the photon, you get a positive, an increase in frequency is a positive Doppler shift. When the phonon is moving away from your photon, you get a negative frequency shift. That's a classical way of interpreting that. Now that you have this, what's going to happen is my pump and my Stokes signal, let's just take the Stokes for example, are propagating in opposite directions in a waveguide. They're going to beat. The intensity of the overall electric field is a beating pattern. But this beating pattern, because of the two frequencies are different, is moving in space. This beating pattern now is an intensity field moving in space. This has an effect called electrorestriction, which is you induce dipole moments, and the dipole moments like to go to the regions where the field is more intense. That's what happens here. So this intensity grading drives furthermore the phonons that were initially at thermal equilibrium. This gives rise to more scattered light, and the more scattered light interferes even more with the pump, and the process builds up. Okay, so it's a feedback process where you amplify this Stokes scattering through electrorestriction and this grading effect, which we often call photoelasticity, nothing but the fact that phonons modulates the refractive index of light because you're modulating the density of the materials. Okay, so one application of that's very neat is this. Let's say I send two pulses counter-propagating in a material, right? The blue pulse and the red pulse. As they propagate in time, they will eventually find themselves superposed inside the material. When they find themselves superposed, if their frequency shift, they generate this beating pattern, the grading that I just mentioned, and they will generate a phonon. So let me show you this in animation here. So the pump pulse comes in, the Stokes pulse comes in from the other side, they find each other at some point in space. At this point, they generate this grading. The grading drives an acoustic wave. The acoustic wave grows. The key thing is light and acoustics propagate at very different velocities. So what's going to happen is long after the optical pulses are gone, the pump and Stokes are gone, the acoustic field is still in the material. You see here? So you can actually store this optical information in the mechanical domain. Remember I mentioned the beam splitter interaction? You can actually get a quantum state of light and encode this quantum state into the mechanics. But the mechanics leaves orders of magnitude longer than light. So the coherence of this mechanical systems allows you to use this as a quantum memory for optical states. And later on, you can do the same protocol to recover back this quantum state that is restored in the mechanical domain back into the optical domain. So this is one of the neat applications of this. And of course, a lot of people are working on this area with different targets. One is quantum memories that I just described. I'm not going to dive into the other ones, but it's a very active field of research as well. So just to give you a glimpse of how you design these things, let me show you one recent example that we picked a material that is very popular but have not been yet explored in this region, which is lithium niobate. So we built a chip of lithium niobate, and we're going to do this brilliant experiment where we're going to send light in the forward direction, a pump mode. We're going to look at the scattering in the backward direction, and in order to phase match forward to backward, you need a phonon that has a very long wave number, right? Energy phase matching or momentum conservation. You need to have this phonon to bridge this momentum gap between the forward going pump and the backward going pump. And we can do that with different polarization states. So this is a way to look into how this acoustic field could actually convert or beam splitter into one polarization of light into another polarization of light. So these are the two spatial fields that you get for this particular waveguide. This is a horizontally polarized mode we call TE, and this is a vertically polarized mode. And we want to interact between this mode and that mode. This is an isotropic material, so this is kind of possible. If you recall your Physics 101 lecture on the guidance of acoustic waves, it behaves pretty much like light. You need to have a material to have total internal reflection. You need to have a material that has a lower velocity in the core and a higher velocity outside. This is what we're going to give rise to total internal reflection, okay? So I'm illustrating this here. So if you're not giving that, you're going to get leakage, right? Every time the surface, the acoustic wave bounces off your material, part of it is radiated, so that long coherence time that I just mentioned is not going to happen. So when we work with this backward Brillouin interaction, because of the large momentum of the acoustic wave to phase match forward-going photons to backward-going photons, means that the same wave is actually propagating with a very shallow angle in this surface. And this allows you to reach the total internal reflection regime and thus guide acoustic waves. And guiding acoustic waves means I'm going to increase the interaction length and also the lifetime of this acoustic wave. I'm not going to dive into the details, but lithium niobate is a nonlinear polar material, so it has a permanent electric moment. So it's used in various applications for that. For example, it has piezoelectricity. It has a Chi2 nonlinearity because it's non-central symmetric, and this is a material that has been really a cornerstone of new applications in integrated photonics. But let me talk about the acoustics. So if you want to guide light, it's an isotropic material, so you need to look at the orientation of your crystal and figure which orientations and what are the velocities for each acoustic wave depending on the orientation that you have in your wafer. So you're sitting on your wafer, depending on whether you rotate your wafer or your waveguide along the wafer, you need to take care of this orientation. So we choose a cut, which is called a Z cut, okay, that gives this sort of slowness surface. How the acoustic velocity depends on direction. I'm not going to dive into the details of that, but we can work out these numbers and find that, yes, for lithium niobate, there is a situation where the shear wave, a wave that propagates like this, actually lies at a lower speed than the substrate underneath. So you have potential for guiding these waves in the material. You need also to work out the photoelasticity in a tensor, in a crystal material. You need to work out what are the right directions to propagate. But if you do that, you can find a situation where the gain for this brilliant process, and all I want you to pay attention in this process is that how you define the gain is a overlaps, a matrix element, if you will. It's a matrix element between your optical fields and your mechanical fields, right? If you have the right symmetries and the right spatial superposition, you get a large matrix element, a very large Brillouin gain. And we found that lithium niobate is just a very strong material, actually one of the most materials comparable to silicon for this particular effect. So it's very good, but it's also anisotropic, so allows you to switch the polarization state of light, as I pointed. I'm not going to dive into this experimental details here, but essentially is you're sending light from one side and asking how much energy is transferred from this optical field into that optical field as they propagate along. And the mechanism of energy transfer is this phonons. Light is being scattered from one frequency to the other through this acoustic wave that has the frequency difference of the two optical fields. So what you get in the output is a field that was amplified over the propagation distance with a given gain. Right? This is how it looks in the lab. This is a chip with a 5 millimeter window here. Okay, so that's all I wanted to convey on this side. You can actually find these mechanical modes that have this sort of zigzag pattern here. They're doing this, so it's propagating in the direction of the board. And we found that this sort of shear wave actually couples the X polarization state with the Y polarization state through this XZ shear component of the motion. And this is very important if we want to be able to switch the polarization states of light using this interaction. Okay, so just one slide on perspectives on this, where we are heading to with this application. So, and to connect as well with the photonic molecules that I just described, a very neat application for this is called Brillouin lasing. Okay, this is one of the processes that allows you to do this very strong electro-optic conversion or microwave optic conversion that I just described. And the idea here is going to build a resonator whose frequency separation, optical resonator, matches the mechanical frequency. If you do so, you can actually very strongly convert pump photons into Stokes photons and lead either to, when its transfer rate of photons is larger than the resonator loss, you get a lasing system. So this is an acoustic induced lasing. Some people call it phonon lasing, if you will. Okay, that's one of the directions we are pushing for. And the reason this connects with photonic molecules that I just described is how you build a resonator whose frequency separation matches a mechanical frequency. So these are frequencies of 10 gigahertz, 6 gigahertz. It requires a millimeter long optical resonator in order to have a frequency spacing of the order of gigahertz. So the idea here that we're pursuing now is you couple two resonators, very micrometer scale resonators whose FSR would be terahertz, hundreds of terahertz, but their coupling strength gives a splitting frequency, avoided crossing between these super modes. And this avoided crossing can be controlled by their gap. And when we do so, we can actually have a micrometer scale resonator, but it has the two optical modes that will support this transition between the pump and the Stokes photon, and thus lead to a very strong microwave to optical frequency conversion. Okay, so just to wrap up, on the care side, we've been looking into this photonic molecules as a way to control your spectral properties and thus enable, for example, generation of squeezed states without being contaminated by these frequency combs that are always present in these devices. Another aspect that we've been really looking at recently is spontaneous symmetry breaking that's related to these bifurcation processes in these structures. And on the Brillouin side, the optomechanical side of things, we've been trying to develop devices that allow us to operate with very large efficiencies for this optical to microwave conversion processes. Lithium niobate is one example of that. And what we've been trying to do right now is exploring this optomechanical interaction to produce, for example, to explore phonon addition and subtraction with light. So I mentioned you create a phonon and you destroy a phonon. So if you start a given, let's say, a thermal state, the Brillouin process is actually adding a phonon to the thermal state or subtracting a phonon. And this leads to non-Gaussian states. Okay, so we are looking into production of non-Gaussian states for various applications in quantum information science based on this process. Finally, I'd like to acknowledge the team at Campinas and collaborators abroad. So a lot of this lithium niobate work, I had a PhD student that was doing BEPI fellowship, is like an internship at Marco Longcher's group at Harvard University. That's where they fabricated these devices and we characterized them in Campinas. Also Thiago Alegre, that is really a lifetime partner on this topic. And more recently, Natalia Tomasi, which just started her professorship career at the University of São Paulo, but led all this work on the photonic molecules at the University of Campinas. And this is everybody together at the Center of Photonics at Unicamp. It's not just my group, but we have about 30, 40 people there working in this in correlated areas of integrated photonics and optomechanics and so on and so forth. And before I close, I'll just leave you one advertisement and perhaps food for thought on funding science in Brazil. So FAPESP created a program a few years ago on quantum technologies. This program was committed to give us about $30 million US for 5 years, about 150 million reais. So it started early 2024. We had 3 calls for proposals. One that completed already. We funded 5 $1 million US startup packages for young researchers that are just arriving at São Paulo. We also run the consortium, it's called just like a INCT-like style research collaboration that we are funding 2 10 million reais projects. These are 2 big groups. The results are not announced yet, but they're coming up probably next month. And we just had the deadline for a very, very productive call for proposals that had 9 applications. It's a combination between FAPESP and FAPERJ. And this is funding, each state is going to fund 5 3 million reais projects. And the message I want to bring is that when we look at the number of applicants and excitement of the community to, access these fundings, tells us sometimes the problem that people say, oh, people ask if you have the money, will people come? And the answer, I think, from this, the lesson learned from this 3 call for proposals is yes. If you put the money available, people will arise from all over the world interested in getting a tap into that. So I was discussing with Rafael all these funding issues, right, that of course affects this place and all other places in Brazil. But I think this is an inspiration, and FAPESP is willing to make partnerships with other state agencies as well. So it's a matter of discussing. So if somehow Rio Grande do Norte state agencies is interested in setting up a partnership somehow with São Paulo, maybe this can be discussed and formulated in a way that similarly to what FAPERJ did, and was we don't know the results yet, but we had 9 applications for this, and I'm sure it's going to be a very qualified application, I must say. I'm sure it's going to be a huge success. And if you're curious, these are the guys that earned the startup funding package. We attracted people from Maryland, JQI, U of Nottingham, Tampere, ETH Zurich, JQU at Linz, that came to Brazil, returned to Brazil to start their careers given this opportunity. So with that, I'd like to close and thank you all for the attention.
Okay, thank you, Gustavo. Let's open for questions.
Thanks, Gustavo. So about this easy machine, so what is encoding each spin there, actually?
So it's the phase of the oscillator. So because it's a binary, so once it goes over the threshold, the OPO, it oscillates either with a 0 phase or a pi phase. So you're going to encode the phases of the optical field into the spins, right? Or the spin's going to be encoded into the phases. So the up spin is going to be a pi phase, and the down spin is going to be a 0 phase.
Right, but they can also be in superposition, or it's only up and down? It would be like a classical...
So you can operate this. A lot of the applications are operating the classical regime because essentially they are coherent states once they oscillate. So you can, of course, make a superposition of 2 coherent states, but it's not a quantum superposition, right? So what you can do, what people have been looking at is whether you could operate with established couplings between these spins that generate, for example, entanglement.
Yes.
So this has been, so is engineering of the coupling matrix. That's the part that has been, and one way of doing that you're oscillating in a cavity. So people encode the multiple spins in the time domain. So think of it like you have a closed resonator. Each pulse, you send a sequence of optical pulses, and each pulse will have a spin. So they're propagating in time, but eventually one pulse goes a round trip and another pulse gets in. But eventually they overlap in space inside the same nonlinear crystal. So we have a Chi2 type of interaction, like SPDC type of interaction, that you can use to couple the two spins. And people have been very clever on using classical technology to extract pulses and inject pulses into this cavity so you can make any topology of your spin coupling. Because this is also a criticism. If you can do only nearest neighbor couplings, trivial, right? In 1D, you have analytical solutions. But if you can start now mapping spin 1 couples with spin 3 or any sort of other topologies in the coupling matrix, that leads you to problems that are really interesting in terms of solid state physics complementarity. So yeah, it's a very, there are a lot of open questions and challenges that have already been identified. But for example, finding the ground state, right? The idea here was if you just increase imagine you have an energy landscape and you set the couplings such that the lowest lying eigenmode is your spins aligned along one direction, for example, all oscillators in phase. Like when you couple pendulum, right? One of the fundamental modes when you have a set of coupled pendulums are all of them oscillating in phase. So if you could do this energy landscape with the coupling such that the ground state is this state, all you need to do is to crank up the pump power and get the system to oscillate, because the first state that it will oscillate is the fundamental state of your Hamiltonian. So this is one example where people are trying to find minima in problems that can be mapped into easy Hamiltonians. And there are a lot of work doing to like NP-hard problems that can be mapped, like graph partitioning and other things. So there are problems there, but the idea for a small number of spin, it works really well. People have demonstrated up with 2,000 spins or 2,000 oscillators coupled, and it can solve problems much faster than classical, let's call it electronic versions of the algorithm with the same encoding have been able to do. So I think it's 1,000-fold faster that you can do. But again, at larger number of spin, there are issues that appear, bifurcations, symmetry breakings that apparently hide this fundamental eigenstate. So people have been asked, are you really able to scale this up and still use this technique to find the fundamental mode of your Hamiltonian or not? But it's been a very active field, I would say.
Question's quite general. You mentioned creation of, for example, entangled states with photons. So what are the usual bottlenecks or problems with, basically performing quantum computation with photons?
So I would say photonic quantum computing, I would say if you're not interested in universal quantum computation, probably that's one of the most mature approaches for quantum computation. For example, the Gaussian boson sampling, where it's not entanglement, but explore correlation and squeezing, right? You generate you start with a squeezer. So we use one of these resonators to build a squeezed state. And the squeezed states go through a unitary, which is essentially a set of interferometers. And you can then, if you can map this quantum problem that you want to solve into this interferometer, which is programmable, you can get a solution in problems such as vibronic spectra of molecules, for example. And this has been demonstrated. People have been able to solve rather large spectra of molecules spectra of rather large molecules using photonic computation. But then the question arises, how universal is Gaussian boson sampling, right? How far can you go? And some people criticize, saying, look, this is really not a push to the point that it's worth building such a computer if that's the only class of problems that you'll be able to solve. So, but if you compare the different kind of quantum computers we have nowadays, for the quantum computers based on photons are the ones that operate at room temperature. They don't need refrigeration. They allow you to scale using this sort of platform, so you can build really large I think the record is 16 modes. So you build 16 squeezers to meet your problems, but there are very clear routes how to scale this to maybe 128 to 156. So there are companies in that direction. For example, Xanadu in Canada is doing that. It's a startup working on this field. Also PsiQuantum in the United States. But again, I think as a criticism to all quantum computing companies, right, it's still unclear whether these problems will get to the size that they are really useful. And I have my own questions on that. I'm not sure if we're going to see this anytime soon. But at least for a physics, I like to see it as a big experimental physics project, that you don't need to get into the Nobel Prize for that or to find the answer to dark matter. But along the way, even if you don't find the answer to the big problem, which would be building a fault-tolerant quantum computer, you do find a lot of stepping stones along the way that are very useful for not only physics, but also technological applications. So that's my hope, that we're going to find a lot of very interesting stepping stones in the process of pursuing quantum computation. I like to be really resilient in saying that we're going to see that either from photons or from other kinds of systems. That's the non-quantum computing guy talking about it, okay? Don't.
Hi, thank you for the very exciting presentation. You just said that these photonic quantum computers will be in principle scalable, but wouldn't that be also a matter of whether or not one is able to implement quantum error correction on them? And these are actually scarce for bosonic systems.
Yes, you're absolutely right. At some point, we're going to tap into that. We are still in the NISQ era, regardless of talking about photons or ions or neutron atoms, right? But I think there's one push, I think, from when you're trying to build going towards universal quantum computation. I think that's more of a problem. But if you're just looking at Gaussian boson sampling, for example, as a subset of quantum computing problems that you can tap into, the scaling there is mostly limited to losses that you can push in this kind of integrated photonic system. So 128 bits modes is possible. Going beyond losses will be a problem. And eventually, you're going to need to tap into quantum error correction. So again, I like to think of this as a platform where you're going to learn new physics rather than a platform that is going to solve the cryptography problems or even the large-scale molecular dynamics problems, because all of them will still suffer from the lack of scalable quantum error correction, right? And I'm not selling it as one platform that's going to work, okay? I'm just saying that for the small scale problems, it's a technology that's very easy to implement. It doesn't require all the fancy fridges that you need for superconducting qubits or the very advanced laser manipulation schemes that you need for atom. So in a way, it's easier to scale in terms of technology than it is with the other platforms. But again, error correction will be a bottleneck at some point, right?
Thank you.
More questions? If not, let's thank Gustavo again. Sorry. 9.
Hello. Yeah, thank you for a nice talk. I was thinking about the optomechanics that you showed. When you have like an optical beam and then you said you can have the mechanical beam that carries the memory of the optical beam for a long time.
Mm-hmm.
You could use that to test some non-Markovian quantum models, something.
I'm not sure if I tap into that. So okay, you can encode this optical state into the mechanical state.
Yeah.
And you're looking into how the system dissipates. That's where the Markovian side of it you're getting. I'm not fully into that, but as far as I know, there are groups working into the thermodynamics of this dissipation process, and one of the aspects that has been explored is in the systems, you are allowed to modulate their properties in time. So instead of having just a thermal reservoir-driven dissipation process, you can engineer how this dissipation is evolving in time. So you can modulate some of the parameters of the systems like a time-dependent Hamiltonian kind of approach. And by engineering this time dependence, you can look into divergences of the standard relaxation process. But I'm not familiar with someone looking specifically into non-Markovian aspects of it. But yeah, I'm sorry, I can't tap into that with more detail. Yeah, I'm not aware.
No, okay,
But we can discuss. I think if you have ideas on what exactly you would be looking for, that I would be happy to discuss that.
Discuss that.
Yeah.
Thank you.
I think that's just a general comment based on your question. I think coming to a solid state fundamental science institute like this, this is something that I've seen happen in the literature and not so much in Brazil, is a very strong bridge between fundamental physics and experimental physics, especially in more techy sides like quantum photonics or integrated photonics. I mentioned this to Rafael because he has a very good example of how these collaborations can be very productive with Fabio, right, in Italy. And if you have people that are thinking to very fundamental questions, and if we have systems that can implement those, I think this is really a great opportunity for collaboration. But somehow, I think it's funding driven, because in the US, the fundamental theory will often be pushed to the edge to get funding and say, hey, why don't you collaborate with someone doing more applied science and try to build something unique? I think that happening much more often than we do here in Brazil. So I think I hope we can address this through future interactions with this institution. Yeah.
Okay, thank you.
Okay, more questions. Then let's thank the speaker again.